Okay, so okay, that's good. So this is the first question. I mean, I'm gonna work something here because that was recorded earlier. But let's see, the span of the question is if you have a vector given in this form 5t, 7t, so it's like negative 571 multiplied by t. This is a vector in R cube. And the question is this in the span of, find a vector V so that H is a span of V. So first of all, looking at the span, what does span mean? Span means taking all the linear combinations. For example, if I'm spanning one vector, if I'm looking at one vector and span of that particular vector is just the multiples of that vector in both the directions. So that the line, let me show. So the line along that vector. Now, in this case, there is only one vector, which is negative 571. And this is multiplied by t. So t is any variable. Now, if we have more vectors, let's say v1, v2, v3, then the span of any given set of vectors, let's say this is vk, so span of any given set of vectors is nothing but the linear combination of those vectors, all linear combinations, all possible linear combinations. So for example, you are adding vectors, you are subtracting vectors, you are multiplying by scalars and so on. So, so I apologize, this recording was done earlier, so I'm just speaking on the top of it. So this is the concept of a span, and whenever we talk about span is actually always a subspace. Now, why span of any vector, any set of vectors, 1, 2, 3, any set of vectors is always a subspace. Whenever you see the word span, it means we are talking about a subspace. So for example, if this is my big set vector space, that's the big space like R cube, R square, all of these are vector spaces. And if you have read, we need 10 axioms to prove that it is a vector space. Like addition of vectors have to be back, scalar multiples should lie in that space, zero vector should be in that space, distributive property, commutative property, all those kind of things that happens to be in R cube, generally R to the n, any n, those are your vector spaces, C to the n, those are your vector spaces. Now, if I take a small subset in that big space, and this subset is the question is, does this subset also act like a space itself? So there are three things that you want to verify. The first one is the addition of two vectors must be back in that set. If I pick two vectors in the small circle, then the addition must be back, zero vector must be back, and then the scalar multiples must be back. If these three criterion hold, then the smaller subset also acts like a subspace. Okay, so the three criterions I'm writing here, given any set of vectors, the addition is back in the space, the scalar multiples are back in the space, and also the zero vector is also back in the space. So if I ask you whether this is a subspace, the first thing is, if I'm writing it as a span of certain vectors, it's clearly a subspace, because the way span is defined, addition is in there, scalar multiples are in there, zero vector is in there. Or you can also check any of these, also check these three properties. If these hold, then that vector is also subspace. Now let's look at an example. For example, R square, and I take this one vector, which is the unit vector along x-axis, right? So my big space is R square, the two-dimensional space, xy plane, and I'm spanning 1, 0. So I'm basically taking all vectors in the direction of x-axis, right? Negative and positive. So basically, it is a subspace. and the subspace is actually my x-axis in this case. Clearly, when I write the span, it is a subspace. But what kind of subspace is this? That's my x-axis right here. Okay. So you add two vectors, you're back on x-axis. You take scalar multiples, you're back on x-axis, and also zero vector is on x-axis, right? 0, 0 origin is on x-axis. And I'm taking the span of this vector, unit vector 1, 0. Even if you take 2, 0, it's still the same. The main thing is this component must be 0. If you are adding scalar multiplication, this component still stays 0, right? So now let's see what I have more. Now this question is, what did I say here? So even what I'm saying is negative 1, 0. The 0 vector isn't there because if you add these two, you get 0 vector. Also, you know, 0 times 1, 0 is also a 0 vector. So all these three criterion are satisfied, and also I've defined it as span. It must be a subspace of R square. So the point is, when I write the word span, automatically these three criterion are satisfied. Okay, so let's go back here and look at this vector. So can I write this set with t as any variable, with t as any constant? Can I write this set as a span of one vector? Yes, I can write this as span of this vector, which is negative 5, 7, 1. So if my v is span, if my v is negative 5, 7, 1, which is given here, so this set can be written as t times this, t times the given vector, negative 5, 7, 1, and which is your vector in R cube. I apologize, there should not be any t. So if I write just the span of negative 5, 7, 1, that's the subspace we are talking about here, the set here. That's the subspace, and it can be written as this span of negative 5, 7, 1, and hence it is a subspace. Okay, because we can write it as a span of a vector. Now let's go back. Let's go to the next problem, which is W is a set of all vectors of the form shown on the right here. Let me change this to sketch. So W is the set of vectors like this. Now, can I find two vectors? Can I extract two vectors from this set and write W as a span of those two vectors? Once I have written that, I know W is a subspace. Okay, so clearly you can see one are the multiples of B and the multiples of C here. If I write one vector as a multiple of B and one vector as a multiple of C, then span of those two vectors right here will be your subspace, right? So let's see what I can do. I don't know what I was talking here, but anyways, so I'm going to decompose this into two vectors. The first one is the coefficients of B, which is 3, negative 1, 0, because I don't see a 0 here, times the B, plus C, it's negative 8, 0, and 2, right? So I'm decomposing this as this. So basically, if you see here, I'm taking the span of these two. The B and C are just constants, right? Arbitrary constants, real numbers. So basically, I'm taking the span of, I'm defining this as V1 and V2. So I'm taking this, the span of V1 and V2. So this set can be written as span of negative 3, 1, 0 and negative 8, 0, 2. So these two are the same. When I talk about span, it means I'm talking about this. And the U and V are, they have said U and V, I define them as V1 and V2. So U and V are given like this. So that's the subspace of R cube, since I can write them as a span of two vectors. Okay. So as long as the word span, I insist, as long as you can write a set as a span, it's automatically a subspace. Okay. So let's go to the next one. Again, very similar. I'm not going to spend more time on here. It's the two vectors, one with the coefficients of S, one with the coefficients of T. So that set can be written like this. 4, 3, 5, 0, and 4, 0, negative 5, 5, right? So again, you have two vectors. This is a subspace of R to the fourth, and I can clearly find two vectors for which this set can be decomposed as S times the first one, like the parametric form that you have seen before, right? So S times the first vector and T times the second vector gives you this set, and S and T are any arbitrary constant. They could be 0, they could be 1, they could be negative 1, and so on. Okay, now this is an interesting example. So W is a set of all vectors of the form shown on the right. Find a set of vectors that span W, or give an example or an explanation showing why W is not a vector space. So this is your homework 8, problem 4, and that's an example of something that's not a vector space, not a subspace. Or I cannot write this as a span of some vectors, right? So you can see there is a presence of this constant right here, constant 1 right here that I have circled. For a subspace, I need 3 things. Addition of vectors must be back, scalar multiples must be back, and then the 0 vector. But when we talk about addition of 2 vectors, if I take 2 vectors of this type, the first one will be minus a plus 1, a minus 5b, and 3b plus a. So this guy right here is still 1, right? That has to be 1 fixed. Second vector, I'm just choosing a1s here. So writing the same thing plus all the same coefficients, just a is replaced with a1, b is with b1, add them. If you add them, what do you get? Let's move to the left side. I get, if you look here, look at this number right here. If I add these two ones, I get a 2. My addition is no longer back in the same set. I need 1 here to be back in the same set. But if I'm adding here, I am not getting 1, I'm getting 2. So first axiom or the first property for a subspace fails here, right? So this is not a vector space. Whenever you have a constant here like +1, +3, -1, that can never be a subspace actually. Okay. Also 0 vector is not in there because of the presence of 1 here, I cannot have 0. If I put a equals 0, b equals 0, I still get 1, 0, 0, not 0, 0, 0. So any of the properties you can show does not work. The 0 vector is not here, or the addition is not satisfied because of the presence, because of this 2, which we want it to be 1 for that particular set. Okay. So anything, any of the axioms or any of the 3 properties that I listed before, if it fails, the set is not a subspace. And usually, if you see +1, +3, +k, any constants here, those kind of sets are not the subspaces. Okay. And you cannot write this as a span of vectors also. If you want to go back and think about this as span, you cannot write this as span of 2 vectors, span of any set of vectors. If we write the coefficients of A's, I know it's -1, 1, and 1. Sorry, this is 1. I'll fix this. So next is 0, 5, 3. This is 1 actually, this guy right here. And then these 2 are A's and B's. I cannot throw in 1, 0, 0. This is wrong. Because I'm not taking multiples of this. This 1 right here is a constant. So this set is not a span of this. This is something else. This span is something else. Okay. The first 2 vectors, okay, I agree. But this 1, 0, 0, it has to be fixed 1. I'm not multiplying it with any other scalars or any other thing. Okay, so this is a good example to see that all the sets are not the subspaces. Okay, so let's see if I have to say something else here. Otherwise, I'm just going to move it further. Okay, so that's not the span. I crossed it out. That's good. Okay, so the next is, okay, let's go to the next one, which is right here. Nathan, any question? Okay, Nathan, are you still there? Okay, so far so good. Okay, I'm going to talk about this problem now. This is my previous recording actually. So I'm trying to voice over, which is kind of it's kind of not very pleasant, but still we can probably I can manage. Okay, so this question is this is your fifth question. It's given the space of matrices, 2 by 2 matrices, under the usual operations of addition and multiplication. So determine if this set is a subspace of M2 by 2. So this is the set I'm taking. Now the difference here is this set has 0 here. Uh, so all the matrices 2 by 2 have A, B, C, D, but this guy has a 0 in there. So basically we are talking about upper triangular matrices here. So the question is, if I add these two matrices, is it still an upper triangular? If I take scalar multiples, are they uh, still upper triangular, and also zero vector or zero matrix is in this set? Those are the three axioms I need to verify. Okay. So if you look at the matrix, if you add two of these, one second, probably I was stuck at somewhere. If you add two of these matrices, this entry will still stay to be 0, right? So if you have A1, B1, 0, D1, and then A2, B2, 0, D2, and you add them like a regular addition, because it says usual operation of addition. So if you do that, then this still stays your 0, right? So that's the first axiom which holds. The second is your, I don't know what I'm talking about here. Let's see what comes here. The second is your scalar multiplication. If I multiply this by any scalars, so the scalars come here, CA, CB, this will still be 0, and CD. So let's see what I'm doing here. So first matrix I'm still adding here. So I'm taking two elements from this kind of set. So I have to make sure that I have 0 in this entry. If I add them, it's still 0, right? So addition is okay. I just need 0 here, that's it. So these are upper triangular. And similarly, if you do lower triangular, they also form a subspace. If you do diagonals, they also form a subspace. So the next one I'm going to talk about is scalar multiplication, I believe, CB. If you multiply with the scalars, this is still 0, which is good. So still upper triangular, which is what we want. And then the 0 matrix is also an upper triangular matrix, right? I'm just concerned about this guy right here. That should be 0. That's it. So 0 matrix is also in the set. So all three axioms are satisfied. Hence, this is a subspace. Okay. Similarly, you can talk about lower triangulars, and also we can talk about your or diagonals as well. They all are subspaces of the big set. Okay, let's move to the next one. A vector is any element of a vector space. That's true. So true by the definition of a vector space. And let's see. Okay. And then if u is a vector in a vector space, then -1 times u is same as the negative of u. Is this statement true? Yeah, that's true. Because each u in V, there is a vector negative u in V. No, I think it's part B. Let's check B first. It's not B, it's DB or D. True, because each u in V minus u. Okay, let's see. I think it's either B or D. I don't remember which one. I think it's true because of each u in V minus u is minus 1 times u. I think it's D. So yeah, so it should be D because this negative u is minus 1 of u right here. So it's not this one because there is a vector minus u, but minus u is defined as negative 1 times u. That's how we define the negatives in a vector space. Okay, so minus of a vector is minus 1 times scalar multiple of minus 1 times u. A vector space is also a subspace of itself. Again, true. You can figure out why. Because the conditions of a subspace includes all axioms. Yes, not axiom. Because all the axioms include the conditions for being. Because the conditions of a subspace include all the axioms of being a vector space, right? Sorry, because the axioms of vector space include the conditions for being a subspace. So part D for that one. Okay. Anyways, the next